Swayam Prabha. Digital India. Educated India.
less than epsilon, then I am ensuring that 1 over square root of 2 sigma t minus t0 plus 1 over x0 square is also less than epsilon, right? Because I will write it incompleteness. This happens. Right? This is less than norm x or absolute value of x0, that is less than epsilon, right? So what does it mean? It means that I can choose delta exactly equal to epsilon, and then we are done. And if I choose delta exactly equal to epsilon, it means that my initial conditions will start within the epsilon ball. And if initial conditions start within the epsilon ball, I am guaranteed that the solutions which are smaller than the initial condition are also within the epsilon ball. So I can in fact choose delta equal to epsilon. So note that this is independent. I mean, we didn't even have to work for it. This is independent of T0, right? So what does it mean? It means that, yeah, it means what? It means this is uniformly stable. Okay, this is uniformly stable, right? Now, what can I say about attractivity? Well, I mean, attractivity is rather straightforward, right? I mean, as I keep increasing T here, this is going to go to 0, right? It doesn't in fact matter what initial condition I choose, not at all. It does not matter what initial condition I choose, it is going to contribute here. Sure, it's going to contribute here, right? It's going to contribute here. But irrespective of what is the size of this, irrespective of the size of this quantity, this is definitely going to blow up to infinity, right? And you're going to converge. This solution is going to converge to the origin, right? So in attractivity, it's just in fact obvious that it is globally uniformly attractive. Yeah, it's globally attractive, sure, right? And the fact that it is uniformly attractive is also evident by the fact that you have a t minus t0, right? It doesn't matter. So this bound on this x0 is first of all global. In fact, so whenever it is global, uniformity does not have to be thought of, because delta is obviously all of Rn, or all of R in this case. Therefore, it is obviously uniform also. Yeah, because the whole idea of being uniform is that the bound delta depends on T0. But if the bound is all of R, then it depends on nothing. All right. So obviously it is globally uniformly attractive. Now, if I combine these two properties, global uniform attractive and uniformly stable, then what do I get? I get globally uniformly asymptotically stable. Okay, not just globally asymptotically stable, but it is globally uniformly asymptotically stable. Okay, so this is a rather nice example. I mean, because we could actually solve it first of all, and of course it has a rather good set of properties. It is globally uniformly asymptotically stable, right? So the origin is globally uniformly asymptotically stable for this system. Okay. Excellent. So let's look at the next example, right? So we are looking at a bunch of examples to get a good feel for what stable systems, what asymptotically stable systems, what I mean, and then so on, what attractive systems, what do these look like? So this is a sort of a second order system. X1 dot is x2 and x2 dot is minus x1 minus 2 over 1 plus tx2. So this is a sort of second order system. Now, if you look at the solution, the solutions look something like this. So this is, of course, I mean, let me be clear again. Yeah. Let's see. Okay, I think the solution is created in this case, assuming that x10 is x10 and x20 is x20, like this kind of a notation. All right. And if you have these initial conditions, these prescribed initial conditions, you have this sort of a solution. Right? This is what your solution looks like. Right. Um, I have to sort of look at this example again. I will verify this later on. But this sort of a system is non-uniformly asymptotically stable. Okay, it should be evident to you that it is definitely converging, because again 1 plus t is going to go to infinity as t goes to infinity, and therefore all these terms are going to go to 0. So attractivity is definitely rather easy. Yeah, and it also has stability. We are not uh, really proving it here, yeah, because it's not going to be very easy to prove in this particular case. Yeah, but you can sort of look at the phase plane portraits, try to draw the phase plane portraits, yeah, and you will find that this is non-uniformly asymptotically stable. So it is in fact stable but not uniformly stable. Okay, so you don't have uniform asymptotic stability. All right, so this is another such special case, and this happens usually when there is a time dependence here, right? Then this sort of tends to happen. Okay, when there is a time dependence in the right hand side, you sort of get some kind of non-uniformity in your asymptotic stability properties. All right, this is pretty standard. All right. So what about the next system? Right, this is the sort of a really favorite linear scalar system example. Very simple, right? So this is sort of x in reals, and x t0 is x0. Okay, so this is the sort of very simple scalar linear system example, and the solution of this is of course very well known to everybody. Yeah, and it essentially looks like this, right? It is x0 e to the power minus kt minus t0. Okay, and we of course claim that this is exponentially stable, right? Because if you simply look at your what happens with your uh, just look at your definition, right? What is the definition for exponential stability? In fact, let's look at global exponential stability, a linear system, so rather straightforward. Okay, so global exponentialist requires the existence of just some constants a b such that your solution satisfies this exponential decay for all t0 greater than equal to 0 and for all initial conditions. And so you can see that if I choose choose a equal to 1 and b equal to k, then satisfies global exponential stability condition. Okay, satisfies the global exponential stability condition. Okay, and so this is of course globally exponentially stable. Okay, uh, so this is in general true for linear time invariant systems. You have some really nice properties, of course. um, the first property for general linear systems is that asymptotic stability is equivalent to stability plus the state transition matrix. So in case folks, you all of you have forgotten the notation, so suppose I have a system of the form x dot is atx, okay, with some initial condition. So this is what is a linear system, right? It is time varying, but it is a linear system, right? Then in this case, the solutions are written as using a state transition matrix as phi t comma t0 x0, where phi is of course the state, called the state transition matrix. So all of you are expected to have seen this. If you're not, please revise this terminology and notation for linear systems. So all linear system solutions can be written in this form, where this is a state transition matrix. Obviously, again, it should be evident to you that phi t0 belongs to n by n. So if where x belongs to Rn, right? So this is an n by n matrix. Right? This is an n by n matrix map which maps initial conditions to the current value of the state. So as you plug in different t here, you get the state at that particular value of time. This is what is a how linear system solutions are written. And so for asymptotic stability, notice that we require stability and attractivity, right? And in this case, attractivity is denoted by this, and stability is just written as stability here. But in fact, there is an equivalent characterization of this also, which is some written here, right? For linear system, stability is actually something like this. All right, so this is actually what it means. Sorry, let's go here. So this is actually equivalent to having absolute value or norm of phi t0 less than kt0 and limit as t goes to infinity phi t0 is 0. So this is the stability part and this is the attractivity part. Okay, this is the stability part and this is the attractivity part. Okay, so these are sort of equal. There are simpler conditions, if you may, if you want to call them simpler conditions, right? So so this is actually LTI in this case, right? So slightly simpler conditions for linear systems. Yeah, so stability is not just a generic epsilon delta sort of condition, but and neither is attractivity, but it is sort of codified in terms of the state transition matrix. So all these properties can be sort of codified in terms of the state transition matrix. Okay. So the other thing we say is for LTI systems, that is linear time invariant system. So what is a linear time invariant system? That is so LTI. I'm going to make this bigger again so I can write. So LTI system is just x dot equals ax, and here we don't even care about writing an initial time. Well, fine, I will write it just for the sake of it. And in this case, the solutions x of t can be written as x of a t minus t0 times x0, right? Where of course this is the exponential of a matrix, and this is the exponential of this matrix, right? I hope all of you know what is a matrix exponential. So in this case, if I get uniform asymptotic stability, right? If I get uniform asymptotic stability, so of course I have two things. I have stability. So I need a couple of properties. In this case, this will be, you know that UAS in this case is equivalent to e to the, because this is of course the state transition matrix. So this is equivalent to e to the power a t minus t0 less than some k t0, and also limit as t goes to infinity e to the power a t minus t0, again in the norm, is equal to 0. Okay, all right. And if this is it's not difficult to show. I mean, this is not really linear systems intensive course as such, but it is not difficult to show that and this you should know also from your typical frequency domain knowledge, that this can happen if and only if uh, real parts of all eigenvalues of A are strictly negative, right? And so solutions, all solutions are exponential decay. Yeah. So this is all. I mean, there's a lot of linear systems theory in this that comes in. Uh, if you are so interested, I can even tell you about it. Right. So any matrix A can be, of course, written in its Jordan form. So real Jordan form, if you may. Um, P lambda P inverse, where lambda is, of course, the um, Jordan block, called the Jordan block. Yeah. And so e to the power a t minus t0 can actually be written as p e to the power gamma t minus t0 p inverse. Okay. And if real lambda is less than 0, right, this is equivalent to real lambda gamma less than 0, because eigenvalues don't change under this sort of a similarity transformation. Again, something that you should know from linear systems theory, right? You have something like this. So all your solutions actually look like xt is p e gamma t minus t0 p inverse x0, right? So if you actually redenote your states as z equal to p inverse x, then this solution is zt is exactly e to the power gamma t minus t0 z0. And for certain, I mean, just to keep the discussion simple, um, we know that for certain cases gamma is a diagonal matrix. It's just the eigenvalue matrix. I mean, just to think of it simply, if there are no complex eigenvalues, this is just a diagonal matrix containing the eigenvalues, right? It's just a diagonal matrix containing the eigenvalue. For the exponential, uh, so diagonalizable cases, what happens? Your zt looks like e to the power minus lambda 1 t minus t0 e to the power minus lambda n t minus t0 z0. Okay, for the diagonalizable cases, you have something like this. Okay, and even for the non-diagonalizable cases, only the real part matters, right? So diagonalizable cases, of course, this is real, right? So for the non-diagonalizable cases also, only the real part matters. Yeah, the complex part really just contributes to sinusoids and all. It doesn't change the magnitude of the solution. So z is, of course, converging exponentially to 0, as you can see, right? Because all of these lambdas are sorry, this is actually positive. uh, the way we have denoted it is lambda 1 lambda n 0 here and 0 here, So we know that all the lambda i's are negative, right, by our assumption. And all of these are negative, then of course z is going to 0 exponentially. So implies z goes to 0 exponentially, right? Because you can look at the expression. So implies, of course, that by this transformation, that x is going to 0 exponentially, because x is just z scaled by some constant matrix p. Okay? Therefore, we are done. Right? This is, we just show, we started with asymptotic stability, and we took this sort of convergence property. And from this convergence property, I know that all the real parts of all eigenvalues have to be negative. And then I can reduce A to its Jordan block form. Yeah. And which is, and then we know that, it's diagonalizable with this, eigenvalues lambda, of which the real parts are anyway negative. Right. So therefore, Z is going to 0 and X is simply P times Z. Therefore, that is also going to 0 exponentially because of this expression. These are all exponential decays. So uniform asymptotic stability for LTI systems is actually just exponential stability. LTI systems cannot do anything but exponential. Okay, excellent. So what we saw today were a few more examples of these notions of stability, right? And in the end, we also sort of try to understand how these conditions simplify or become a little bit more specific for linear systems and linear time invariant systems, where solutions can be written using the state transition matrix. All right. So we will continue further on this discussion of stability next time, and we stop our discussion for today here. Thank you.